Hello FNH 161, this is Liz. We are now going to start one of two lectures on the balance concept. This lecture is on fluid balance, and then the next one will cover pH balance. As we're talking about fluids, I want to start with some context or big picture ideas. So I think we all know that water is very important for our bodies and that about 50 to 80% of our body is made up of water. Water is not only important for getting rid of wastes in urine, as we just learned about, but it's also important for transport, for supporting our cells, lubricating joints, allowing us to absorb nutrients and move things through the gut, regulating our body temperature, moistening our eyes, making compounds, and protecting our vital organs and tissues. So clearly, maintaining our water or fluid balance is essential for homeostasis and life. So in this lecture, we are going to start off by learning about the balance concept. And to do that, we have to define what we mean by the internal pool and inputs and outputs from the body. We'll then talk about this balance concept and what it means to be in stable, positive, or negative balance. And then we'll look at our body fluids. We'll start by identifying the different body fluid compartments, and then we'll discuss how we maintain fluid balance. And when we're talking about fluid balance, there's two key things that we want to control. First is our extracellular fluid volume, or how much fluid we have. And that is controlled by maintaining sodium balance. So we'll talk about sodium inputs and outputs and how we maintain our sodium balance. Then we also want to maintain how concentrated or the osmolarity or tonicity of our extracellular fluid. And we maintain this by controlling water balance. So we'll look at some inputs and outputs of water and how we maintain water balance. And finally, we'll talk about what happens when we cannot maintain the ECF tonicity and when our extracellular fluid becomes too concentrated, hypertonic, or too dilute, hypotonic. So let's start at the top with this idea of inputs and outputs from the body. So if I'm going to maintain balance in my body, I need to understand where things are coming in or going out. So in terms of inputs, we add things to our body through ingestion, that's eating or drinking, inhalation when we breathe in air. We can also take things in through our skin, not as big of a route, but we can absorb certain medications and things through our skin. And we can inject things into our body. Then for outputs, we lose materials through our urine. We just learned about how we make urine and the importance of making urine. We also lose through our feces. When we exhale, we lose material in our secretions, for example, in our sweat. And we also lose material in some sloughed off cells, particularly our skin cells that turn over quite frequently. So at its simplest, the balance concept suggests that what we put into our body needs to equal what we take out. Now let's add a little more complexity here. So when we're talking about our body, what we're meaning is our internal pool, or what we have in our extracellular fluid, in our blood and the fluid around our cells. So we have an internal pool of many different substances. This could be water, it could be glucose, it could be iron or another mineral or vitamin. Now we can add to that internal pool through those inputs we just listed. So ingestion, inhalation, absorption, or injection. but we can also add to it through metabolic production. So for example, we produce water through cellular respiration. Now, from our internal pool, we can lose things through our outputs. And those are the outputs we just listed through our kidneys and urine, lungs and breath, through our digestive tract or our body surfaces. We can also lose things as we metabolically consume them. So for example, with our respiration, we use oxygen and we're going to produce carbon dioxide in water. So again, the balance concept suggests that these inputs, which includes both what comes into our body from outside and what we produce, should equal our outputs, what we lose to our external environment and what we consume in the body. Now there's one more layer to add here, and that is storage in the body. So we do have stores of some things like, for example, iron. So that if your inputs don't match your outputs, you can take some iron from your stores to maintain that internal pool. All right, so now let's talk more about this balance idea. So the balance concept says to maintain a stable internal pool, which is what we want to do as a grown adult. We're not changing size, we're not growing any bigger or smaller. We want to be stable. The total inputs of a substance must equal the total output. So stable balance, input equals output. Now, to maintain this stable balance, if I increase my input, I have to increase output. So for example, if we think of something like our fluid intake or water intake, if I increase my intake, let's say I drink more, so I increase my input, to maintain balance, I have to output more, which means I have to produce more urine. In the same fashion, if I decrease my input, so let's say I drink less, I will also decrease my output or make less urine to compensate. Now for this one, I said to an extent. So important note here is that when it comes to increased input, our body is pretty good at getting rid of excess. So I can drink quite a bit of water and my body fairly easily gets rid of it in urine and sweat and other things. But if I decrease my input, my body can compensate a bit. So let's say there's a day where I didn't have much water, I'm probably just not going to make as much urine. But if I never drink water, every day I'm losing a bit of water, my body can't fully compensate for that. So eventually I will become dehydrated to the point that that could be fatal. So we can only compensate for decreased input to an extent. Maybe a few days of not drinking as much water as we should. Now, what happens if we don't maintain stable balance? When we consume more than our output, we're in positive balance. So one of the ways to imagine this is to think about energy. So when we consume more energy than we burn, we're in positive energy balance, and the body is going to show that through weight gain. That extra energy is going to be stored on the body. In negative balance, our inputs are less than our output. So that would be I'm eating less than I'm burning. And the body's going to compensate by stealing extra energy from my stores. And that's going to lead to weight loss. So there are times where we might want to be in positive or negative balance. Energy balance being one. Someone who's growing does actually want to be in positive balance. But in general, a healthy adult wants to maintain a stable balance of most things. So let's try some clickers here. So if JW consumes 1,500 mLs of water and excretes 1,500 mLs per day, what state of water balance are they in? This is stable. their inputs of 1500 equal their outputs, which means that the amount of water in their body is staying the same. What if they increase their water intake to 2 liters? So input is increased to 2 liters. What happens to their output to maintain balance? They'll have to increase their output to 2 liters as well. So any increase in input has to be met with an increase in output. Now, what if KW consumes 400 per day? So input 400 and they excrete 500. And if you'll remember from the start of the urinary system, 500 is actually what we call our obligatory losses. So it's the minimum amount that we can lose. We have to excrete that amount per day just to keep the body functioning. So even if you don't consume very much water, let's say only 400, we still have to excrete 500. What state of water balance are they in? Well, input is less than the output. That is negative water balance, or we're losing water every day, and that could very quickly lead to dehydration. Okay, so that is the balance concept. Let's now relate this to fluid balance. And when I say fluid, I'm not just talking about water, but it's water and the substances dissolved in it, such as the electrolytes. Now, the amount of fluid in our body varies among individuals. So I might have a different amount of fluid than you. And it also varies across tissues. For example, the fluid in the liver is different from that in the brain, that in the bone, etc. But across one individual, total fluid is fairly constant. So the amount of fluid that I have is maintained because the kidneys and hormones are working hard to maintain fluid balance. In other words, these systems are constantly working to ensure that my inputs equal my outputs. Now, before we talk about that, I just want to circle back to this idea. The amount of fluid varies among individuals. Let's try clicker question here. So the main determinant of the percent of total body weight that is water is which of these? So the main determinant of your percentage of water is not how much water you consume, not your blood volume, and not even how much skeletal mass you have. It's actually the amount of fat tissue you have. The reason for this, if we look at the fluid composition of different organs, we'll see that most of our organs are somewhere around 80% water by weight. So brain, blood, liver, kidney, they do vary somewhat, but somewhere around 70 to 80% water. Our bone has less, but our adipose tissue or fat tissue has substantially less water, only 10% water by weight. So if someone has a lot more adipose tissue, they essentially have more dry or water-free, fluid-free tissue. So more adipose tissue means less body water by percentage. Okay, so our body fluids, the total body fluid on average is about 40 liters, but as we just said, this will vary from individual to individual. It's roughly about 60% of our body weight, but again, can vary anywhere from 50 to 80%. Now, of that body fluid, most of it is intracellular, inside of our cells. That's about 2/3 of our total fluid. The remaining 1/3 is extracellular or outside of our cells. Of that, only 1/4 is in our blood plasma. And the remaining 3/4 is in our interstitial fluid or the fluid around our cells. So if we take these and look at some actual numbers, and note this is not examinable, you do need to know the different compartments and about how much each compartment is. You don't need to know the actual volumes. But for fun, let's say our total body fluid is 42 liters. Now, of that, 2/3 is in our intracellular fluid, so 28 liters inside our cells, which leaves only about 14 liters outside of our cells. Now, of this 14, 1/4 is in our blood plasma. So we think of blood as where most of our body fluid is. It's really only about 3.5 liters of your total 40 some odd liters. The interstitial fluid makes up the remaining 3/4 of about 10 liters. Now we also have some other negligible amounts, lymph being the fluid in our lymphatic system, and transcellular fluid being things like our spinal fluid, our fluid in our joints, things like that, that really the total amount is negligible compared to the total amount of fluid in our body. Okay, if we look at the composition of our major body fluid compartments, so that's our intracellular fluid, and the example here is muscle because it will be slightly different in each of our organs or tissues. Then our interstitial fluid around our cells and our plasma. What you should notice is that the blood plasma and interstitial fluid are quite similar in composition. Lots of sodium, chloride, and bicarbonate. And this is because the plasma and interstitial fluid are separated by the capillary wall, which remember is quite porous and allows most things, especially these small electrolytes in water, to pass through. Now, clicker question for you. So pause, answer, come back. So the key factor determining the movement of fluids from the plasma to the interstitial space is the blood pressure. So if we think about our capillaries, so here's my blood and my red blood cells, and then around it is the interstitial fluid. Remember that these are exchanged by that bulk exchange process that is mostly determined by net pressures, the biggest one being our blood pressure, which forces fluids outwards into the interstitial fluid. So that's the main factor that controls this. Now, plasma proteins and the hydrostatic pressure of the interstitial fluid also plays somewhat of a role in the reabsorption of fluids, but blood pressure is the key determinant. Now, if we compare our extracellular fluid with our intracellular fluid, we can start to see some pretty stark differences. So in the extracellular fluid, we have a lot more sodium as the main positive ion, whereas inside of cells, we have a lot more potassium. The main anions or negative electrolytes outside of cells are chloride and bicarbonate, and inside of our cells, we have phosphate and some proteins. So clearly much bigger differences here. And the reason for this is that where the plasma and interstitial fluid are separated by this very porous capillary wall that allows things to pass very easily, what's inside of our cells is separated from the outside by the plasma membrane. And the plasma membrane is a selective barrier that can control what goes in and out of our cells. Now, these ions, for example, have to go through ion channels, and we can close or open these to maintain this difference in ions. Water can pass through this membrane, Remember, how water moves is by osmosis. So the key factor that determines water movement between the inside and outside of cells is osmolarity or osmosis. Now, clicker question. The key factor determining movement of water between the ECF and the ICF inside of our cells is the osmolarity, because water moves by osmosis. If the ECF is usually kept around 300 milliosmoles, what's the typical ICF osmolarity? So the answer here is it's the same, it's 300. Now we keep the osmolarity of the ICF and ECF the same so that there's no net water flow. So water goes in and out at about the same rate. Now if we were to, let's say, increase the osmolarity of the ICF to 400 and the outside was much lower, water likes to go where it's more concentrated, where there's more solutes. So that would mean that we'd have net water going into the cell and our cells would swell and possibly burst. So we keep the osmolarity the same. Now we'll come back to this concept when we talk about water balance, but I do just want to highlight here a common misconception. So although the electrolytes, the type of ions in the water is So although the composition of the fluid differs, the outside having more sodium and chloride and inside it's more potassium and phosphate, the total dissolved substances or the osmolarity is the same in the ECF and ICF. And that allows our water to just go back and forth without filling up our cells or dehydrating our cells. Okay, so quick recap here. We said we have three main fluid compartments: our intracellular fluid, our interstitial fluid around our cells, and our blood plasma. And these two collectively are called the extracellular fluid outside of cells. Now, movement of fluid between the plasma and interstitial fluid is quite free. We exchange things quite freely because there's a lot of pores in these capillaries. And the main determinant of how much we exchange is that bulk flow or blood pressure. And we maintain blood pressure through how much blood volume we have, or the ECF volume. Now, in order to maintain our volume, we need to maintain sodium balance. So it's a little counterintuitive because you think that ECF volume would be just drinking more water, but it's actually sodium that's the key regulator here. Now, going between the cells and our interstitial fluid, we said that water moves by osmosis. And so to maintain that, we need to maintain our osmolarity. And osmolarity is maintained through water balance. So more simply, there are two key things we need to maintain: the volume or total amount of fluid we have, and we maintain that through sodium balance. And then how concentrated that fluid is, or osmolarity, and we maintain that through water balance. So the rest of this lecture will focus on these two concepts, and we'll start by how we maintain blood pressure and ECF volume. Now, I happen to know that you know a little bit about blood pressure, as we did talk about this in the circulatory system. So what's going to happen when blood pressure is too high? So I'm going to come back and draw my blood capillary again. And remember, the main determinant of the exchange between our plasma and interstitial fluid is the net filtration pressure, which is mostly determined by blood pressure. So if our blood pressure goes up, we are going to have more pushing out of fluids from the plasma or more filtration. And that could possibly lead to edema. So when blood pressure is too high, we'll filter more or move more fluid from the plasma to the interstitial fluid. So we want to make sure that we maintain an appropriate pressure so that we get fluids to our tissue, but not filtering out too much. Now, short-term regulation of blood pressure occurs through which of these? So recall that we talked about very short-term control of blood pressure happening in seconds, and then more long-term control. Our short-term control was the sympathetic stimulation, increasing cardiac output and resistance, because we said that our mean arterial pressure is cardiac output times resistance. So we're going to beat our heart faster and harder, we'll constrict our vessels, and that will bring our blood pressure up. Now this is short term, and this can only hold us off for so long. If our blood pressure is too low in the long term, we really need to have control of our blood volume, which we're going to control through our glomerular filtration rate and the RAS system. So blood volume is more of our long-term control. Now, in order to control blood volume, we need sodium balance. Sodium is the key solute that regulates our ECF volume, which in turn maintains our blood volume and our long-term maintenance of blood pressure. So if we hold on to more sodium, we're going to hold on to more water. So our ECF volume, the total fluid we have, goes up. That means we have more blood volume and more blood pressure. Less sodium, less water follows. We have lower blood volume and blood pressure. So key to understanding this is that wherever sodium goes, water will follow. So instead of regulating the water part here, we regulate sodium, and water comes along naturally, increasing our total fluid volume. So how do we maintain sodium balance? We have to come back to what we talked about in the beginning in this idea of inputs and outputs. We will maintain sodium balance when our sodium inputs equal our outputs from the body. Sodium inputs really only come from ingestion, so what we eat or drink. And this is not well regulated. So you might crave saltier foods, but your body doesn't actually have a way of saying, hey, that's enough sodium, or no, you need to eat more sodium. So we kind of just eat to our taste preferences. We're not really doing this based on sodium balance. In terms of outputs, the main one is going to be the sodium we lose in our urine. And we'll also lose some in secretions like sweat and our feces. Now, sweat and fecal losses also not well regulated. We kind of lose whatever we need to lose, which leaves us with urine as the key regulator of sodium balance. Urine, or our kidneys, our renal system, is the key regulator. Now, fortunately for you, you've just learned about how our renal system regulates sodium balance, and we'll do a quick review of that in a minute. But let's start by looking at this side, our sodium inputs. So we get sodium by consuming sodium. Now, which of the following represents the recommended intake for sodium, so how much we should be eating, and how much Canadians on average are actually consuming? So the answer here is A. So sodium recommendations are written as something called an AI, an adequate intake, which is the amount we should aim to consume. We should be consuming about 1,500 milligrams per day, but on average, Canadians consume almost double that. Now, this other number, 2,300, is actually what we call the CDRR, or Chronic Disease Risk Reduction Value, which means that we should be consuming less than this amount to reduce our risk of chronic disease, like hypertension, cardiovascular disease. Now, as you can see, most Canadians are consuming substantially more than that. Even more exceptional when you think about this being the average, the 50th percentile. So there's people consuming much, much more than this. The number one way that you are going to decrease your sodium intake is by decreasing your intake of processed foods, highly processed foods, because that's where most of the sodium is hiding in our diet. Changing the amount of salt you add at the table or seasoning you add to your foods could have a minor effect, but it's really the processed foods that are giving us these very high numbers. Now, if someone consumed more sodium than they excreted, what type of sodium balance would they be in? So if our inputs were greater than our outputs, which is where many of us are with these high sodium, highly processed food diets, that puts us into positive sodium balance. Now, in the case of sodium, positive sodium balance would lead to increased ECF volume and increased blood pressure. And then we wonder why high blood pressure or hypertension is such a widespread issue. Now, it's a bit of an oversimplification. There are many factors that contribute to high blood pressure, genetics being a big one. Activity, diet is just one component. But certainly our very high sodium intakes, largely from processed foods, are not helping. So clearly sodium intake is not well regulated. Many of us are consuming more sodium than we actually need. Most of the regulation of sodium balance occurs through the kidneys and the amount of salt we excrete in the urine. Now, as we just did the urinary system, you should know how we regulate sodium balance by adjusting the glomerular filtration rate. So that was through the sympathetic nervous system. And that we regulate tubular reabsorption of sodium. So how much we reabsorb through RAS, or the renin-angiotensin-aldosterone system. So make sure you can draw out each of those or explain each of those mechanisms out. So just briefly reviewing, if our blood pressure went down, our body compensates by activating the sympathetic nervous system that causes vasoconstriction of that afferent arteriole and decreases the blood flow into the glomerulus in the glomerular filtration rate. So now we will be filtering out less sodium, which means we excrete less, we hold on to more, and the more we hold on to, the more water follows, and that keeps our blood volume and blood pressure up. We also regulate sodium balance through the renin-angiotensin-aldosterone system. Aldosterone acts on the kidneys to promote sodium reabsorption. So not only are we filtering out less from the blood, but of what we do filter, we will reabsorb more. So that means we're going to excrete less and hold on to more sodium. And wherever sodium goes, water will follow. So we will bring back our sodium, bring back our blood volume, and our blood pressure. All right, so do make sure you know all of the steps in these two pathways and recognize that these two mechanisms are happening at the same time to control sodium balance. Now, one thing to note is that A lot of these figures we look at talk about what happens when our blood pressure goes down or sodium is too low. And that's because our body has good mechanisms to deal with these, because if we couldn't, this would be fatal. But as we saw in recent clickers, the bigger concern in modern environments is not that we have too little sodium, but that we have too much. So when sodium levels increase, how does the body respond? Well, we just do the opposite. Instead of reabsorbing more, we are going to excrete more sodium by filtering more and decreasing how much we reabsorb. So we'll just get rid of it as much as we can. Now, obviously we're not perfect at this because a lot of us have elevated sodium and elevated blood pressure. So it's not a perfect mechanism. Okay, moving on now. So where blood pressure and blood volume was the main determinant of movement between the blood and the interstitial fluid, movement between the extracellular fluid and intracellular fluid occurs by osmosis. And so our osmolarity is the main determinant of water movement between the ECF and the ICF. Now, under normal physiological conditions, the ECF and ICF are isotonic. So they both have an osmolarity of about 300 milliosmoles per liter. So even though they have different solutes, the total dissolved solutes is equal in the cells compared to outside, so that water moves back and forth, but there's no net osmosis or no net movement of water into or out of our cells. Okay, before we go on to how we maintain osmolarity and water balance, I want to just go over one of the tricky concepts here, and that's this idea of isotonic changes in ECF volume. So we've been talking about how we maintain sodium balance to maintain our ECF volume and blood pressure. Now, when sodium changes, water always follows. And so we get more fluid in, but because there's sodium there too, we change the volume but not the concentration. Essentially, we're getting fluid that's at the same concentration as the rest of our body fluids. So we're just adding volume but not changing the concentration. Now, when we're not changing the concentration or the tonicity, there's no net movement across the membrane or into or out of cells. So water goes back and forth. So long as we don't change the concentration out here, there's not going to be net movement into the cell or net movement out of the cell. Movement between the ECF and ICF only occurs when we change the osmolarity. So if we change sodium, we change the volume, but not the concentration or osmolarity of the fluids coming in. So we say this is an isotonic change. We're adding fluids that are the same tonicity as our body. Now, as we'll discuss, when we change water, we are going to change the osmolarity. We're going to either dilute what's in our body, or if we don't have enough, we'll make it more concentrated. And only when the osmolarity changes do we have movement of water across the cell. Let's put this into practice. So, if someone is given an isotonic intravenous rehydrating solution, so if you go into the ER or if you're in the hospital for whatever reason, they'll likely give you an IV of saline. That's isotonic, the same tonicity as our body fluids. What will occur? Well, the answer here is D. So if we're going to add fluids, the volume of our ECF will increase. We'll have more fluids in our body. But because it's the same tonicity, we're not changing the concentration. So we still have 300 milliosmol inside and outside. Even though I add more fluid here, we're not going to be putting more fluid into our cell. The only thing that would cause more fluid to go into our cell is if we change the osmolarity. So ECF will increase, so we'll get more fluid here, but the ICF volume will not change. Now, what if someone was accidentally given an IV of a hypertonic, so a solution that was too concentrated, more concentrated than our body fluids, and the osmolarity of the ECF increased? So now we're thinking about our cell that's 300 milliosmol, and let's say I gave you a very concentrated solution and the ECF went up to 500 milliosmoles. Now, this is going to cause net movement of water across the cell. Change osmolarity, change movement across the cell. In this case, water always likes to go to where it's more concentrated. So it'll leave the cell trying to dilute this very concentrated extracellular fluid. So fluid will move from the ICF to the ECF and our cells will shrink. All right, I have a few more practice questions on that concept at the end of your course notes, and we can go over those during our live class as well. Let's now move on to how we maintain ECF osmolarity, which is via water balance. So sodium maintains ECF volume. To maintain osmolarity, we want to maintain water balance. And water balance is where our water input equals our water output. So what are the water inputs? Obviously, we get water from the fluids that we drink. We also get water from our foods, quite a bit actually, especially foods like our fruits and vegetables. They're very high in water. We also metabolically produce water. So during our cellular respiration, we are going to generate some water. Now our outputs can be divided into what we call our sensible water losses. So these are ones we're aware of. They make sense. So that's the water loss in our urine, the water that we lose in our feces, and the water that we lose in sweat. Probably three that you were likely aware of. We also have what we call our insensible losses, which are losses that we're not always aware of. So this is the water we lose through our lungs every time we breathe, and the water that we're losing from our skin even when we're not visibly sweating. So let's start by going through our water inputs first, and then we'll talk about the outputs and water balance. So for water intake, the current recommended intake level is 2.7 liters for adult females and 3.7 liters for adult males. Importantly, this is water from both fluids and food. So it does not mean that you have to drink 2.7 liters of water per day. It means that if you are drinking some water, but also eating a lot of foods that have water, like fruits and vegetables, for example, for a total of 2.7 liters, then you should be fine. Now, some clickers here. Do your intakes of coffee or other caffeinated beverages like Diet Coke or tea contribute to your water intake? Yep, they absolutely do. So that 2.7 liter, it's not just fluids like water, it's also fluids like coffee, juice, soda, all those things. Is coconut water more hydrating? From the perspective of water intake, water output, coconut water versus regular water are really not different. So it's the same thing. The difference would be that coconut water would also have some electrolytes or some solutes, which really shouldn't be of a big concern unless you are working out very strenuously or working out under very hot conditions where you're sweating a lot more than normal. then you might want to consider adding in electrolytes with your water as you're losing a lot of sodium in sweat. So that's where something like coconut water or a sports drink might be relevant. For most people, anything that contains water is good enough. All right, so let's put some numbers to this. So for our water inputs, fluid intake on average is about 1,250 mLs. So again, you don't need to be consuming the full 2.7 liters as water, about 1,250 mLs of fluids, and we get about another 1,000 milliliters from the foods we eat. We produce about 350 milliliters of water per day, which leads to a total input of 2,600 mLs. Obviously, large variation here. We're looking at just averages. But let's say your total input was 2,600, then you'd want to balance that with the same outputs. So this would be about 900 milliliters of those insensible losses that we're not really aware of, 100 from sweat, 100 from feces, and about 1,500 mLs on average from urine. Again, highly variable. You might be sweating much more. You might lose a lot more urine to compensate for increased input. We're just looking at averages here and how they can be balanced. Now, for regulating water balance, which of those sources of water input and output do you think we actually regulate or control for the purposes of maintaining fluid balance? Now, the answer is E. For inputs, we only regulate the amount we drink. For outputs, it's only our urine. So coming back to this, let's say I'm dehydrated. What's my body going to tell me? It's going to say, you're thirsty. You need to drink more. Doesn't usually say, hey, you need to eat more. That's more of a hunger issue. And we can't control how much water we metabolically produce. So fluid intake is the one we regulate on the input side. And then for outputs, we can't really control how much we lose through our lungs, through our sweat, or even in our feces. So the main one we control is our output through urine or through our kidneys. So intake of fluids and output of urine are the two mechanisms we use to control water balance. How do we do this? We have specialized receptors called the osmoreceptors, and these are detecting the osmolarity, the concentration of our extracellular fluid. And in turn, they will regulate thirst or water intake and how much water we reabsorb in the kidneys or our urine or water output. Thirst is regulated by a thirst center in the hypothalamus, and water output is regulated by vasopressin, which we discussed when we did the renal system. All right, let's draw out what this will look like. So let's say we had a water deficit. In other words, I am dehydrated. I'm often dehydrated. In a water deficit, our blood plasma will have an increased osmolarity. So it will become more concentrated. This will be detected by osmoreceptors that detect the osmolarity of plasma. And these osmoreceptors are found in our hypothalamus. Now, those osmoreceptors will respond by sending out a signal to us to say, hey, you're thirsty. In response, we will ideally increase our water intake. We'll drink more. And as we consume water, we will decrease our plasma osmolarity, or we'll dilute our plasma, bringing the plasma osmolarity back down. Now, at the same time, these osmoreceptors will communicate with the posterior pituitary to release vasopressin. And vasopressin will tell our kidneys to increase water reabsorption, which means we will excrete less water in our urine. We'll hold more water and dilute our plasma, decreasing our plasma osmolarity. So in a water deficit, increased plasma osmolarity is detected by osmoreceptors. And these osmoreceptors will allow us to increase our inputs of water by increasing thirst and decrease our output of water by reabsorbing less or excreting less water in our urine. Now, there was another factor that can stimulate both thirst and vasopressin. What other factor did we discuss in class? So the answer is angiotensin 2, which was part of the renin-angiotensin-aldosterone system. Now, this is important because it shows you how water and sodium are linked. So if we want to just increase water, then we would just do vasopressin. This alone, this would allow us to reabsorb more water, dilute our plasma. If we wanted to control our ECF volume, we are going to activate this RAS system, which increases our sodium reabsorption. And where sodium goes, we want water to follow. But to help out with that, we also have vasopressin, which allows us to absorb more water to follow the sodium. So they are linked together. All right, what happens if we are unable to maintain our ECF osmolarity? So if we have a deficit of water, so in other words, we're dehydrated, we are going to see an increase in the osmolarity of our plasma. So it's more concentrated. That is going to make our ECF hypertonic, or more concentrated than what's in our cells. And when what is outside is more concentrated than what's inside, water wants to move from the ICF to the ECF to try and dilute it, and our cells will shrink. So dehydration can cause shrinking of our cells. What about if we have an excess of water or overhydration? It's possible. Our osmolarity is going to decrease, and we become hypotonic, or less concentrated than what's in the cells. So now here I've got my cells. It's more concentrated inside. Water's going to move to where it's more concentrated. It likes to dilute things. So water will move from the ECF into our cells, and our cells will swell or expand. They may even, in extreme situations, start to burst. All right, to bring this full circle, let's bring this back to the balance concept. So if someone is dehydrated, or they're in a hypertonic state, they are likely in which of these states of water balance? So dehydrated is insufficient water, that is negative water balance. In other words, our inputs are less than our outputs. So we don't have enough water, we're dehydrated. Okay, so if someone is dehydrated, they are in negative water balance, which means that their inputs are less than their outputs. And because of this, we are going to have hypertonicity, where the outside of the cell is more concentrated than the inside, and water wants to move where it's more concentrated out of the cells. Now we can get into this state by either insufficient water intake. So if our inputs are too low, we're not drinking enough water, or because we're losing too much. So for example, excess sweating, running a marathon on a hot day. Another disorder that causes this is diabetes insipidus, and this is where the body doesn't respond to vasopressin. So despite the body's needs, the person would continue to excrete very dilute urine with a lot of water. Now, what happens here? Well, if our cells are losing water and shrinking, that includes our neurons. So we might see shrinking of our neurons, which can lead to confusion, convulsions, even a coma, as our neurons in our brain stop working. We're also going to have less total water. If you're dehydrated, you have less body water, and that can influence your circulatory system. So you'll have lower blood volume, lower blood pressure. You can run into circulatory shock, where we simply don't have the blood volume and blood pressure to adequately perfuse the brain or pump blood to the brain. This can also lead to things like dry skin, sunken eyeballs, dry tongue, because all of the places that we need water will feel the deficits. What about the other end of the spectrum, overhydration? So this occurs when we are in positive water balance. So our inputs are greater than our outputs. In other words, we're drinking more than we might excrete. In this case, it will lead to hypotonicity. So we're going to be more concentrated inside the cells compared to outside. And water wants to move into where it's more concentrating, causing our cells to swell and even potentially burst. This can be caused by renal failure. So we're unable to make and excrete urine, which is our main way of getting rid of water. It could also be that we are consuming too much water. So it's rare, but it is possible to consume too much water too quickly. Now, what's going to happen? Our cells are going to swell. Again, this includes our brain cells, our neurons. And when our brain cells swell, that's going to lead to confusion, convulsions, coma, lethargy or tiredness, a headache, dizziness, vomiting, drowsiness, possibly even death. We would also feel weakness because the muscle cells begin to swell and they're not functioning properly. So even though it is more rare to be overhydrated, it is possible. Here's an example. A marathon runner narrowly avoids death after drinking too much water. So it is possible to drink too much water. So instead of me just telling you what a safe amount of water is, I have a critical thinking problem for you where you can apply your knowledge, your understanding of the renal system and water excretion to calculate by yourself what the maximum amount of fluid is that the kidney can excrete per hour. In other words, how much can the kidney handle, which tells us how much we can drink to balance those outputs. So if we maximize this, that tells us the maximum amount we can drink. So we'll go over this in our live class this week. All right, to summarize, fluid balance maintains the total volume and distribution of water in our body compartments, which are the intracellular fluid and our extracellular fluid being our plasma and interstitial fluid. In order to control the volume of fluid, the total amount we have, we control sodium balance, and that's mainly regulated through the kidneys that control how much sodium we filter out of the blood and how much sodium we reabsorb into the blood. To control the concentration of our fluid, or ECF osmolarity, we control water balance. And water is both regulated through intake or inputs through our thirst, as well as through our kidneys and how much we reabsorb through the action of vasopressin. All right, if you have any questions, please post on Piazza, or you can ask me during our live class.